Hello, today I'm going to solve the second question of the final exam using the two-stage least squares approach. And you will see that it's much more difficult than the GMM approach. So still I see that many students tried two-stage least squares approach. So you have to understand when you do something, you have to understand if it's the right way, like easy or not, right? So let me start. We are doing the same linear regression like this. And as usual, we have endogenous variable x2 and we have instrumental variable z2. And everything else is the same. But actually, I realized that this notation is not ideal. Like same as GMM, I had to update the notation a little bit. But two-stage least squares approach requires much more notation and setup. Let me try. Okay. So let me start from the basic. Like we have y equals intercept plus beta 10 x1I plus beta 20 x2I plus epsilon I. Okay, this is the standard linear regression model, and I'm going to denote it as xi transpose beta 0 plus epsilon, where xi equals intercept and x1 and x2. It's three dimension, like 3 by 1 vector, and of course beta 0 is alpha 0, beta 1 0, and beta 2 0, which is also 3 by 1 dimension. Okay, so this is the second stage. This is second stage regression, the main regression, and this x2 causes the problem, like endogeneity problem. So we have to make a first stage regression. So first stage regression is about the endogenous variable x2i. We have x2i and we explain this using intercept, say gamma 1 0 plus exogenous variable x1i plus excluded exogenous variables z2 transpose gamma 3. Okay, so these are scalars, but I assumed z2 is m by 1 vector, so after transposition it is 1 by m, and so gamma 3 is m by 1 again. And then here I use this notation zi transpose gamma 0 plus xi, where zi is a vector of intercept and x1, the exogenous variable, and the excluded variable, which is m plus 2 by 1 vector. Okay. Similarly, gamma 0 includes gamma 1 0, which is intercept, and coefficient of x1 and coefficient of the excluded variable gamma 3 0. It is also m plus 2 times 1 vector. Okay, that is the first stage. In here, as you know, we usually define, like, so our strategy is we are going to predict y2 and replace this endogenous variable with x2 head. Okay, we estimate x2 head here and use that for the second stage. That is our strategy. So let me try another form. So then I will define two different predicted values. By the way, one more comment here. When doing this, you have to include, say, in the original regression, these two, the constant term and x1 are exogenous. Then default is include all the exogenous variables in the first stage, right? Unless you have any other reasons not to include them, right? So you have to include these two, in the first stage. Okay. So now I will define additional notation. So we usually define x2I hat as the estimated version. Same thing, all right? Same regression, just predicted value of x2. So of course, gamma hat are the estimator, right? Usually OLS estimator. On the other hand, I will define another notation, say x2I0. Notation is not ideal, but you'll see what I'm saying, what I'm doing here. So I will consider this. So gamma 10, gamma 20, gamma 30 are the true values of gamma. If you know them, you can calculate a better predicted value of x2. But because you don't know the gammas, the true gammas, so you have to use estimators. And you may simplify this to say zi transpose gamma hat. And you may write it as zi transpose gamma 0. Okay, right? That's what you do. And also observe that x2 is scalar, so it is 1 by 1. It is 1 by 1. Okay. You will see that they are different. This is what we used in our class. But when I try this question by myself, I find a more useful notation. The problem is, so bring this back to the second stage here, then you are going to get yi equals alpha 0 plus beta 10 x1I plus beta 20 x2I hat plus error. Okay, so then this replaces the true x2, and this is a new residual, right? And what I want is I want to write it as something like this. If I could write it as vector, that would be great. So I define xi as a vector of exogenous variables as they are, and I'm sorry. So what I define is I will define xi of gamma as x2 zi transpose gamma, right? So this is my definition of. So when gamma is given, you can construct x in this way, so that like using this notation, you can rewrite the second stage equation as yi. If you write yi as, say, 20 x2I hat plus error, can be written as xi gamma hat transpose beta 0 plus error. Okay, so this is what we have, and what we can simplify. We can simplify this term into a vector in this way, and then later it also helps you to differentiate x with respect to gamma. Okay. So far, I defined the required notation. And now then, let's set up the minimization problem. In the second stage minimization problem, we are doing minimize over beta, and I will write it this way. Function L of beta given gamma. I will use this vertical bar to explicitly denote that gamma is given, and it is just a function of beta. We are minimizing with respect to beta only. And Li the function Li, the criterion function, will be defined as for simplicity, I will put 1 minus 1 over like minus 1 over 2 yi minus xi gamma transpose beta squared. Okay, right? This is the criterion function. By the way, if anyone know how to remove this automatically detected, dotted line, I don't know, maybe iPad like recognizes that as a letter, so try to convert it to automatically convert it to letter, but I don't want to do that. Let me know how to remove that. I want to disable that. I don't know how to do that. Anyhow, so this is the familiar least squares criterion function, and I put minus 1 over 2 for convenience. We'll see why we need to put that here. Okay, let's do the differentiation now. So, differentiate Li with respect to beta first, right? And then you get minus 1 over 2 canceled out, and you get xi gamma, no transpose, yi minus xi gamma transpose beta. Okay. By the way, let me explain it a little more. So when you have gamma, it can be, if you know the true gamma, you will use true gamma, and if you have an estimator, you are going to plug that in here. So based on gamma, you are going to generate regressor. X gamma is generated regressor based on the first stage estimate, and then use the generated regressor in the second stage. So when you differentiate with respect to beta, you get this. And just, I need to check, it is 3 by 1 and it is 1 by 1. So it's 3 by 1, the dimension is correct. And here you plug in, oh, what happened? It's gone? Oh no. Oh no. I don't know, it crashed. So, sorry about that. So now I will plug in beta 0 and gamma 0. I plug into this function, plug in the true values, then you will get xi gamma 0, yi minus xi gamma 0 transpose beta 0. Okay, I just replaced gamma and beta with their true values, and it is xi gamma 0 times, here this is epsilon minus plus beta 20 psi I, which we denoted as ui, right? It is 3 by 1 vector. So pretty simple, right? We get a derivative, okay? Simple derivative. Now I am going to differentiate this again. Second derivative. Differentiate L with respect to beta again. So not square, but what I meant is transpose. So we know it should be 3 by 3 matrix, Hessian matrix. Then, like here, if you differentiate this guy again, then it's clear. Minus xi gamma times xi gamma transpose. Pretty simple. And here, if you plug in beta 0 and gamma 0, and you will get minus xi gamma 0 and xi gamma 0 again. And after taking expectation, we define it as h. H is defined as minus expectation xi gamma 0 xi gamma 0 transpose. Remember, it looks like this if you read it write down the matrix x1i and zi transpose gamma 0 times 1 x1i zi transpose gamma 0. So this is 3 by 3 matrix. So we are just using a vector notation. Okay, this is H. We will use them later. And now we are going to differentiate this guy. We start from here to calculate cross derivative, right? The cross derivative before, so to calculate the cross derivative, first think about the dimension. So first differentiate with respect, like L is scalar and beta is 3 by 1. So the number of rows will be 3, and gamma is n plus 2 by 1. So it's transposed. So this will be the last dimension of this cross derivative matrix. And another thing we need to think about is derivative of xi gamma with respect to gamma transpose, right? So it is easy, right? From here, definition of xi gamma, you will get 0, 0, and zi transpose. Check the dimension. X is 3 by 1, and gamma transpose is 1 by m plus 2. So, and in the end, it is it should be excuse me, it should be a lot of zeros. So in the end it should be 3 by m plus 2. So these zeros are actually 0, 0, 0, 0, 0, 0, 0, many zeros, m plus 2 zeros as a row. So this is correct. And now back to the cross derivative here. When you differentiate the first derivative with respect to gamma again, you will get, first I will differentiate outside. First thing, first term goes like this. And next, so I differentiate this guy. And now next I will differentiate this guy. To do that, you will get minus xi gamma times xi gamma transpose, but because of this transposition, we will have to transpose again. So transpose transpose here, and it is not transposed, and times beta. This is the derivative. Okay, it's a simple derivative. Just differentiate here and here. Then next, I will plug in beta 0 and gamma 0 into the cross derivative. Then you will get let me denote this as, say, how do I do it? Say AI, because it does not depend on gamma. So this will be AI times yi minus xi gamma 0 transpose beta 0 minus xi gamma 0 times AI transpose beta. That is beta 0. Okay, that is what we have. And we know this part is ui. We define ui. This is epsilon I plus beta 2 0 psi I. So it will be ui. And minus this part will become xi gamma 0 AI transpose beta 0. Okay, that's what we get here. And now I will take expectation. Take expectation of the cross derivative at beta 0 and gamma 0. Then expectation of u will be 0. So this term goes away. and you have minus expectation of xi gamma 0 times ai transpose beta 0 is what you get, what you have. Okay. By the way, I could simplify this a little more. ai transpose beta 2. So back here, ai is 3 by 3 by n plus 2. So ai transpose beta 0 is, it is m plus 2 times 3 and 3 times 1. So you will get zi times beta 2 0. Beta 0 is alpha 0, beta 1 0, beta 2 0. But here, as you see, AI has all zeros in the first two rows and only non-zero elements in the third one. So when you multiply beta to AI, you will only have beta 2 in the end. So this is the final simplification, and that means you can use that minus expectation xi gamma 0 times, instead of ai ai transpose beta 0, I will use zi beta 2 0. Okay. Let me see if I'm doing it right. Something is wrong. Let me see, because this xi, this is 3 by 1. It is 3 by 1. And this is 1 by m plus 2. Oh, not wrong. Oh no, m2 plus m2 by 1. So I made some mistake. Dimension does not match. So I think I made a mistake here. It should be AI transpose and beta transpose. Beta transpose here and transpose here. Then you don't need to transpose this scalar. So you don't need to do it here. So then let's see, it is 3 by 1. It is still it's a problem. M plus 2 by 1. It is 1 by 1. Something is still not right. So dimension does not match. Let me see. When you differentiate, I was wrong here. So the problem was in here. When I differentiate with respect to gamma here, the dimension must be, it should be, let me erase all these. Minus xi does not have any problem. Outside xi is right, but inside that is, should be go this way. Beta transpose x derivative xi gamma differentiate gamma transpose. This should be right. Let me check. Xi is 3 by 1, beta is 3 by 1 but transpose 1 by 3, and xi differentiated with respect to gamma is 3 times gamma dimension, m plus 2. Okay, this is right. This is right. Everything was my mistake. Sorry about that. And then we are going to fix that problem here. here, and here, and here. So let's do this. This is right, this is right, this is right. So we will just do it beta transpose AI, and beta transpose AI is going to be like here, beta transpose AI here, and then let's simplify this. Beta transpose AI, beta 0 transpose times AI equals literally beta 2 0 times z transpose. So beta 2 0 times zi transpose. This dimension is 3 by 1, 1 by 1, and it is 1 by m plus 2, so it is right. Dimension matching. And then you can rearrange again this as minus expectation xi0, simple notation, and z times zi transpose, and I will bring beta 2 outside of the expectation. Okay, so we spent a lot of time to do all these things, right? So the reason why we are doing this is to derive the, oh, no space here. How can I extend the page? Oh no. I made a new page. So, so we are looking for the influence function for the second stage, the first stage estimator and the second stage estimator, right? Just in case if you don't remember what was an influence function, we want, like when you have an estimator, say beta hat n, I usually use subscript n, its difference from the truth is the estimation error, and we will decompose the estimation error into the influences of each observation. Psi I is theoretically the ith observation's influence on the estimation error, and specifically we are multiplying square root n and assume that the difference is just ignorable. The difference between these two becomes small p1, which means it converges to 0 in probability. Okay, and also the psi I has mean 0. The influence function must have mean 0, and then as you can see, this whole term, this looks very much like a central limit theorem. So the whole term goes to normal 0 times 0 comma variance of the influence function. Okay, that is our purpose to derive the influence function. Okay, same thing. We are going to think about the first stage estimator's influence function as phi, and then we want, first let's derive the phi here. This is the first stage estimator, and that is OLS. So it is well known. We know it is OLS of x2i on z. Z is 1x1i and z2i. Okay, so then phi I, the influence function, looks like this, if you remember, right? Then it satisfies the influence function condition, right? The reason, again, this is the first stage estimation error. All right, we want this influence function because the first stage estimation error, this term, the first stage estimation error will affect the second stage error, right? So we have to think about it, and influence function is really convenient to capture the relationship between the first and the second stage estimation errors. So as a result, the second stage influence function psi takes this form. We learned it in class. H inverse times the first derivative with respect to beta of the criterion function plus g times first stage error, like influence function, I mean, right? And all these things we already calculated. H inverse was minus expectation of xi gamma 0 times xi gamma 0 transpose, right? Its inverse is going there. And in our notation, we may write it as like xi0 transpose for simplicity. And we calculated this equals, I don't remember what was that. So the derivative was given here, right? X times u. Okay, go back to 7. Right? Is that right? No. 7. So here it is xi gamma 0 times ui, right? Which we again use simplified notation. And G was expectation of xi gamma 0 times zi transpose times beta 2 0. Double check. Again, it was here. There was a minus sign. Minus, you have to put minus there. So minus. And finally, phi I is expectation zi transpose zi inverse zi psi I. Okay. So combine those all 4 terms and plug that into here. That's what we are doing. And then let's first calculate inside the bracket, like the parentheses. Then you get G, G, I will rewrite G as, so minus xi gamma 0 can be written as, like beta will be coming in front. This times z0 gamma 0 time transpose zi is what we are going to use here times zi. So when you calculate G times phi I, you will get minus beta 2 0 gamma 0 transpose zi psi I, because this part and this part will be cancelled out. Okay, so we have simplification here. Furthermore, and this again will become minus beta 2 0 psi I times xi 0, right? So that means now if you add this and this, u minus, remember u was epsilon plus beta 2 0 psi I. So when you subtract u, subtract this from u, you will get this is xi minus xi0 times epsilon I. Okay, and then in the end we get psi I as h inverse times minus xi0 epsilon I, but h inverse was this. Minus cancels out, xi0 transpose inverse xi0 epsilon I, right? This is the desired result. So the variance will be pretty simple. I mean, in the end, derivation was complicated. So as a result, variance of the second stage estimator, let me start do it this way. The second stage estimator sampling distribution will be normal distribution with zero mean and variance of psi, right? And this variance is the asymptotic variance, which is based on this, right? So you can write it as expectation of epsilon squared xi transpose xi0 transpose expectation xi0 transpose inverse x let me see the other way. Sorry so expectation of psi prime is expectation of expectation xi0 transpose inverse xi0 epsilon I, and epsilon I xi0 transpose expectation of xi0 transpose inverse. Okay, this is what we get, and in the end you get the sandwich formula xi0 transpose inverse expectation epsilon I squared xi0 transpose times expectation xi0 transpose inverse, right? And this is actually the desired answer. And if you assume homoscedasticity assumption, something like this, then so actually this means you have to write as, so xi0 is our notation, so more rigorously you have to write it as x1i and z2i. It is sigma squared for all I. Then the asymptotic variance becomes sigma squared times expectation xi0 transpose inverse, which is very similar to the OLS estimator. This is the answer to the first, the part A. Okay, so as I said, GMM is much easier, much more theoretically elegant, right? Two-stage least squares is kind of only for empirical convenience, like a practical convenience, but theoretically it's a mess. And that is but I'm not saying two-stage least square is bad. It is useful and it is pretty widely used. What I am worried about is that you don't know what is even more difficult, right? That's what I wanted to say. And then how do we estimate that? How to estimate the variance? So as you see here, when you calculate, let's just use the sandwich formula. When you calculate this, right? So come back here. First, how would you estimate? So we have to start from here. xi0 was defined as 1 x1i, and x2 was replaced by z transpose gamma 0. Okay, so itself xi0 itself is not observed because gamma 0 is not observed. You have to replace it, right? I mean, it's not alpha. Xi hat will be used instead of xi0. The idea is, why don't we just use estimated gamma, right? Replace unknown gamma 0 into gamma hat. Then you can calculate the things. So as a result, that means when you estimate xi0 transpose expectation, then you are going to estimate this using xi hat transpose. Okay, right? Just replace the expectation to sample average. That is another strategy. And then, other than that, we need to handle epsilon, right? So how do we estimate the expectation of epsilon squared xi0 transpose? And then you are going to estimate this as 1 over n summation epsilon hat squared times xi hat transpose, where epsilon I hat is defined as yi minus alpha hat minus beta 1 hat x1i minus beta 2 hat x2i. This is the point. The main, even more important, is this xi is not x hat. Okay, so you have to use original x2. If you use x hat, then you will get ui. Okay, so that is the problem. So when you implement the estimation of the variance, you have to use original x2i, not the fitted value. So I hope it helps. As you see, my conclusion is that why don't you study GMM? Okay,